Well, now we're going to start talking about the graphs of some log functions. And let's start off with a little review about how we come about the logs. Remember talking about an exponential function, example y equals 2 to the x. We want its inverse. And we knew we could find its inverse by point plotting and flipping the x and y's. We also know that we could find the inverse by reflecting the graph across the line y equals x. So the blue graph here is the graph of an exponential, and the red graph is the graph of its corresponding inverse, which we come to call the log. Okay, so summarize down here, the blue function y equals 2 to the x, its inverse is x equals 2 to the y, which is in red, which is written as a log function, log base 2 of x. Okay, so these are our function and its inverse, and this is the logarithmic function. So we're going to look at these functions and recall, particularly want to look at the log graph. Okay, so let's do some graphical analysis. Okay, remember when we were looking at y equals a to the x, a greater than 1. We have this characteristic shape. Okay, we determined that the domain can be anything, but the range is limited to only positives. We know that this has a y-intercept of 1, and it has the asymptote along the negative x-axis. So now we're going to look at the inverse, which would be y equals, it should be equal sign there, y equals the log base a of x, which is going to be the mirror image of this across the line y equals x. Okay, so there it is. All right, and let's study some things, some properties of this graph. Obviously, we know when we take the inverses, domain and range are switched. Okay, so then we'd have to say that the domain here is only positives. Okay, only positives. You can't take the log of a negative number. The range is everything, all values. The x-intercept is at 1, and the asymptote is along the negative y-axis. So a couple things to recall. Domain, only positive values. Can't take the log of zero, can't take the log of a negative. The range, everything. Okay, the x-intercept's at 1, and the asymptote is along the negative y-axis. Okay, so with that in mind, we should be able to come up with some properties as such. Okay, one thing, all right, we know that the log and its corresponding exponential are inverses, but we've already looked at inverses some time ago and found that there is a inherent property in inverses, that is, when you take their composites, either way, it always yields x. So therefore, if we were to assign function f as the exponential a to the x and g as the log a of x, its inverse, then we would know that the composite g f of x equaling x would have to equal x. And the composite g f of x would be log base a of a to the x, which should, okay, just reveal to us x, okay? And that's a property of inverses. And since logs are and their corresponding exponentials are inverses, that must hold true, okay? The other composition, f of g of x, also yields x, and that composition, f, would be a to the log a of x, which would yield us x. So as a consequence of these, we look at the common logs. So we have log of 10 to some power, that's simply x, okay? And 10 to the log x would equal x, okay? That's just the general case example with the common logs. And with the natural logs, same thing. The composition of the natural log and its corresponding exponential, ln of e to the x is equal to x. And the composition the other way, e to the ln of x equals x. Okay? Additional properties that arise as well, kind of resulting from the graphs. Okay? Remember the graph of the log. Okay? Graph of the log had the x-intercept at 1. So therefore, if I put in 1, I should get out 0. So, okay, we have a property that log any base of 1 will always equal 0. So the log of 1 will always equal 0. Okay? To illustrate that, we just say, okay, I don't know what the log base a of 1 is. So I'm just assigning it some variable y. Well, then what does that translate into? That translates into a to the y equals 1, which, of course, anything will equal anything raised to the 0 power equal 1. Therefore, this y value is 0. Okay? Also, the natural log or the common log of 1 is equal to 0. And the natural log of 1 is equal to 0. Just corollaries, if you will, of these things, because it just is the exact same property just applied to the common and the natural log. Okay? What else? Okay? Log base a of a is equal to 1. So if the subscript and the argument are the same, it just reveals 1. And to illustrate that, we'll just say, well, let's assume we don't know what log base a of a is. So we'll call it y, which translates into a to the y equals a. Well, that would imply that y was equal to 1. And then you have the corresponding common and natural log counterparts to that rule. Okay? As you can see, log 10 is always 1, and log e is always 1. Okay? Let's look at how we can construct some graphs of logs. Okay, let's look at this as an example. Y equals the opposite log base 3 of x minus 2 plus 1. Well, a couple things. Okay, we want to find where the asymptote is, we want to find where the intercepts are, and then be able to construct the graph. Okay, now remember, okay, we should be able to right away from this argument x minus 2, we should agree that that is a translation 2 units to the right. Okay, now if we're shifting the whole graph 2 units to the right, that means we're redefining its domain. Okay, it is a reflection across the x-axis. Because of this negative here, and it is translated upward in y. Okay, so let's look at what happens when we translate this thing 2 units to the right. Okay, now remember, you can only take the log of a positive, so that would imply that this argument x minus 2 has got to be greater than 2. Greater than 0, which implies x has got to be greater than 2, which essentially establishes where the vertical asymptote is of the log function. Okay, at x equals 2 is the vertical asymptote for that log function. All right, so that's a start. Now let's look for some intercepts. Okay, we can find the y-intercept setting x equal to 0. But if we set x equals 0, we have to evaluate, okay, the log at a negative value, which is not possible because logs are not defined for negatives. Okay, so therefore, we looking for the y-intercept, we found that there is none. Now let's try to find the x-intercept. Of course, the x-intercept is when y equals 0. So if we set y equals 0, our opening equation results in this expression, okay? And then we can send the -1 to the other side, okay? And then we can proceed to change this out of the log form. Well, I guess we first would clear out the negatives. Then we proceed to change this into log form, which says 3 to the 1 is equal to x minus 2. Easily solve that for x equals 5. So what do we have? We have a log function, okay, as shown here. Okay, we have the at the vertical asymptote at x equals 2, we have the graph defined for all values greater than 2, which is what we determined up here, okay? And we have a y and x-intercept at 5. And there is our graph, okay? And that does it for our consideration of log graphs. We'll have some worksheets for you to help out with your understanding of that. And I'm going to stop it here.